Hello students. In this video we'll talk about the complexity of the algorithms, right? So let's directly move to the next slide and see what do we mean by the complexity of the algorithm. So given an algorithm, how efficient is this algorithm for solving a problem given input of a particular size? So remember, efficiency is one of the property of the algorithm that we discussed in the previous video lectures. So how we can measure the efficiency of the algorithm is that it means for a given input of a particular size, how does it behave, right? To answer this question, we usually ask in two terms, right? How much time does this algorithm use to solve a problem? We usually refer it with the time complexity, that how much time does the algorithm require in order to solve the problem. Number two, second, how much computer memory does this algorithm use to solve the problem? And we refer this with the space complexity. So the two important aspects of the complexity of the algorithm, what do I mean by the complexity? How much time it requires and how much space it requires, right? In this video lecture, we will be focused towards the time complexity of the algorithm, and the space complexity you will be learning in the coming the lectures, especially the data structure and the algorithms, right? Clear? So we will measure the time complexity in terms of the number of operations an algorithm uses, and we will use a big O notation and big theta notation to estimate the time complexity, right? So time complexity, we will build this, we will define a function based on the number of operations, how many times those number of operations are being used on a given input, and at the end we will see in terms of the big O and big theta. So we can use this analysis to see whether it is practical to use this algorithm to solve a problem with input of a particular size. We can also compare the efficiency of different algorithms for solving the same problem. Like I mentioned that there are more than 200 sorting algorithms. So you can compare those algorithms based on their efficiency, based on their big O and theta notations. We ignore the implementation details. Obviously, we do not get into the detail of the software, the hardware, the data structure they use, the programming language and the compiler used. So we are not considered with those limitations. We are not considered with those details. What we are going to do, we will use the algorithm written on a paper, we'll dry run it, we'll see the number of operations, we'll see the size of the input, we'll establish a equation of the function, and then we'll see the growth of that function in order to find the complexity of that algorithm, right? So time complexity, to analyze the time complexity of the algorithms, we determine the number of operations, right? This is important, the number of operations such as comparisons, arithmetic operations like addition, multiplication, subtraction, division. We can estimate the time a computer may actually use to solve a problem using the amount of time required to do basic operations, right? So we'll find the basic operations, then we'll see how many times those basic operations are being executed, and then we'll formulate the equation. So we ignore the minor details. So we don't, focus those details. So we'll focus on the worst case time complexity of the algorithm. And by worst case, I mean by the upper bound. And by mean of the upper bound, I mean by the big O notation, right? So this provides an upper bound on the number of operations an algorithm uses to solve problem with input of particular size. This is really important to see, okay, in a worst case scenario, as the number of input grows, what would be the worst case, what would be the worst behavior, what would be the worst growth of the function, growth of my algorithm, right? It is usually much more difficult to determine the average case time complexity of the algorithm. The average case time complexity is not the average of worst case and the best case, right? Average case time complexity is the number of operation an algorithm uses to solve a problem, exact number of exact number of operations that an algorithm uses for a particular input. That is really difficult to find out. But then it turns out for some algorithm, it is easy to find that. We'll see one algorithm in the coming slides. So if you remember this algorithm that we discussed earlier, that is the algorithm to find out the maximum number from a given list, right? So this is the pseudocode that we have already seen in the previous videos. So describe the time complexity of the algorithm of finding the maximum element in a finite sequence. So how we can do that? See the solution. Count the number of comparisons. What we do, we will count the number of operations. So the basic operation is the comparison operation. So let's see how many comparisons does this algorithm perform. So we see then that max less than AI. Where is that max less than AI? This is written here. How many times this operation comparison is being performed? This is done n minus 1 times. Why? Because I is starting from 1 to n, 2 to n. So 1 is minus. So n minus n minus 1 time this operation, this comparison is performed. Okay. So each time I is incremented, a test is made to see whether I is less than or equal to n. So every time what we are going to do, we are for this loop, the loop starts from 2 to n. So every time the I is incremented, every time we need to compare whether this is I is less than or equal to n or not. So that means this is also n executed n minus 1 times. So one last comparison determines when I is greater than 1. So the loop will terminate when I value becomes greater than n. So the loop will execute for n times, 2 to n, but one more comparison is required in order to check to terminate the loop. So the one extra comparison is performed. So exactly what happens, n minus 1 comparison for to checking the max less than AI, n minus 1 and n minus 1 comparison for I less than n, right? So that means 2 into n minus 1 comparisons are required plus one extra comparison that we require for terminating the loop. So 2 n minus 1 comparisons are made in order to execute this loop. So if you see, this is the f of n now is f of n is 2n minus 1, right? And you can see for which class of this fn belongs, you can always set up that this belongs 2 of n belongs, or f of n actually belongs to the big O of n, right? Where n is the g of n, right? So we always see the least uppercase. Remember, least uppercase. So since this is the big O of g of n, and in a I mean, you in if you remember from the previous video lecture, this is also belongs to the big omega of n, right? Since both are the linear function. So then it turns out that basically f of n is basically the theta of n, big theta of n, right? So this algorithm to find the max number behaves behaves linearly in all the cases, in the best case, in the worst case, and in the average case. Clear? Okay. Next, we have already seen this algorithm as well. This is the linear search algorithm. So we already discussed it in the previous video lectures. So how we are going to compute the complexity here? So let's count the number of operations. How we can do that? So at each step, two comparisons are made. If you see, while two comparisons are performed, I is less than or equal to n and x is not equal to ai. So how many number of times this is executed? Every time we are going to take these two comparisons, right? Okay, then to end this loop, one extra comparison is required in order to terminate I is less. I mean, this will execute until I is greater than n. So one additional comparison is required. So in order to compare this AI, what happens if x is equal to AI, right? If this x becomes AI, this loop will terminate. And for 2i plus 1 comparison are required, right? If in order, if this is right, if x is not on the list, if x is not present in the list, that means if x is not present in the list, that means we will end up the loop by looking at all the list, and 2n plus 1 number of comparisons will be performed, right? so are made, and then an additional comparison is used to exit the loop. So in the worst case, if you compare this 2n plus 1 plus 1 I mean that means 2n plus 2 comparisons are made, and then this is a linear, this belongs to the theta of n, as we mentioned in the previous slide as well. So this behaves linearly as well, the linear search, right? That's why the name is also the linear search. But when what happens if I mean this is the true, this is true, 2n plus 2 is true when the all the elements in the list are compared and the whole list is consumed, and we are going to check I mean we have checked all the list, and the element is not found out, or element is at the last element in the list, then this is true. But what happens if we found the element at in middle, I mean maybe at the second the element is present at the second position or third position or fourth position or fifth position or sixth position or n minus 1th position. So that means the number of comparisons are, I mean there are the equal chance for every position, every location, for that this comparison is performed, right? So just wait. So for the average case analysis of the linear search, every position of the element is equally likely may return the result. So there is the probability that, I mean, this is the probabilistic analysis. Then in the average case for every, I mean, every position, there is a probability that we can find the required element at that position. So here is the example. Describe the average case performance of the linear search algorithm. Although I said it's usually difficult, but in this case it is easier to find the average case analysis. So what happens? Assume the element is in the list, and that the possible position are equally likely. As I mentioned, at every position there is the possibility that we can find the element at any position. By the argument on the previous slide, if x is equal to ai, the number of a comparison is 2i plus 1. We already know that. I mean in this slide we already discussed this one, right? So if it is element is there in the in middleware, so that may be the 2i plus 1. So if we find out the complexity of all those numbers, so for example 1 2 3 4 up to n, all the numbers, right? And if we divide all that's the probability, right? So probability, we already know the outcome. I mean for example for every position, if there are n elements in the list, for example, so there is the possibility that 1 by n chances are for the first position, 2 by n chances are for the second position, 3 by n is the chances for the third position, and so on up to n by n, right? So that means the possibility at every position is same. So that's why what we did, 1 plus 2 plus and so on. This is what, let me just simplify this. This would be nothing but 1 plus 2 plus 3 plus 4 plus so on plus n divided by n, isn't it? If we just take the common, and then this is what, n into n plus 1, isn't it? This is the number of this is the sum of first n number divided by n, right? So when you just simplify this one, this will be n square plus n divided by n, right? And then you will find out that and obviously this whole is divided by n. This is the upper top, I mean this is the numerator, this whole is divided by n. And then when you will simplify this equation, you will find out the answer is n plus 2. And when you will take the upper bound, then this will be I mean you if in terms of the theta, we take the only the variable with the higher order polynomial, that's the theta of n. So in the average case, we perform some additional tasks. That's why usually we say that big O is the upper bound and the worst case analysis, and we prefer to find out the big O and the upper bound of an algorithm, right? So binary search. Now let's see about the binary search. In a binary search algorithm, we know that what happens in the binary search, the list is divided into two equal halves, and if then we find the middle value and we compare the required element with the middle value, and then we'll see where we have to find that, right? So assume for the simplicity, n is equal to 2 into k elements, right? So 2 power k elements, just to make it simple. 2 power k means k is any value 1 2 3 4 5 6 7 8 whatever. So the list contains, if n is equal to 1, contains the one element. So if this is true, then k is equal to log n. Remember the proper taking the log on both sides, right? Okay, so now let's count the number of comparisons. So two comparisons are made at each stage, right? So here you can see I is less than j, right? One comparison, and x is greater than a of m. So two comparison in every iteration of the while loop, right? So at the first iteration, the size of the list is 2k, as we just mentioned here. Size of the list is 2k, and after the first iteration, the size will be decreased 2k minus 1, right? Clear? If at the first the list, the size of the list is 2 power 8, at the next the list size of the list would be 2 power 7. So you can just see the value of the 2 power 8 and 2 power 7, right? Then 2 power k minus 2, and so on until 2 power 1, right? At the last step, an additional comparison will tell us the size of the list, that it becomes 1 here, right? Right? And the element is compared with the single remaining element, right? Hence the more at most 2k plus 2 would be the comparisons, that is nothing but equal to the 2 log n plus 2. So if these number of comparisons are made, how these number of comparisons are made? Based on the upper discussion, that k minus 1 list, and so on, we will I mean do all the list will be reduced to the 2 power 0, and at the end maximum 2 power 2 into k plus 1, 2k plus 2 comparisons will be made. And 2k, if we replace the value of k, we already know the value of the k is log n, that would be 2 log n plus 2, right? And if this is true, this log n is the value of the k, 2k plus 2, and the value of the k is log n, so that becomes 2 log plus 2. And if this is true, and we can see that this is theta of log n, since this is the there is only one variable n that is with the log of n, and we take that log of n, right? So the worst case time complexity of the linear search is log n, right? Let's talk about the bubble sort. So we already seen the bubble sort, right? So in the bubble sort, we have multiple passes, and in every pass, we are going to compare the elements. So a sequence of n minus 1 passes is made through the list. We already know that. On each pass, n minus I comparisons are made, if you remember from the previous videos, right? So that means, so different passes are there, n minus 1 passes are there, and in every pass, n minus I comparisons are made. So that means n minus 1, n minus 2, n minus 2 up to 1, right? Or in another way, we can simply write it, for n minus 1 passes, right? We are going to have n minus I comparisons. So if you simplify this one for some value of I, so for example, I value is, again, let me take the I value as the lowest value, that is 1. So that will become n minus 1 into n minus 1, right? If we take the I as the best case or the worst case, the lowest value of I. So that is nothing but n is into n square minus n minus 2, right? So n square minus 2n minus 2, right? So, and then you take the higher order polynomial, that is n square. Or in the other way, if you compute this one, this is nothing but n into n minus 1 divided by 2. That is, again, you take n square, theta of n square. All right. Okay. Insertion sort, time complexity of the insertion sort. So if you compare the insertion sort, this is similar to the same. I mean, the total number of the comparisons are, so you are starting from 2 to n, right? So basically, if I again substitute the even if you can compare the number of comparisons, right? So number of comparisons are made from 2 to n, 2 3 4 5 6 7 up to n, right? Up to n, that is nothing but the sum of the first n natural number, n into n minus 1 divided by 2, right? And then you are going to divide it with 2 because of the rest of the calculations minus 1. And if you n into n minus 1 divided by 2, if you complete it, that is nothing but n square minus n divided by 2. So that is n square minus n divided by 2 minus 1. And if you just take the higher order polynomial, that is theta of n square, right? That's how we are going to compute the complexity, worst case complexity, big O or big theta of any algorithm, right? So what we have done, we found out that this is nothing but a function. Algorithm is a function, and in the function we are going to check the size of the function, the input, and the number of the operations. Based on that, we are formulating the equation, and we are going to check the higher order polynomial for the worst case analysis. In order to find the big omega, we take the lowest order polynomial, right? Matrician multiplication algorithm. We already seen the matrices in the previous chapter. So if we are going to multiply two matrices, right? Say for example, the definition of the matrix multiplication, we already know C is equal to AB, where C is the M cross N matrix, and A is the M into K, and B is the K into N matrix, right? So this is the algorithm for multiplying the two matrices. So matrix multiplication of A comma B, right? So for I is equal to 1, j is equal to 1 to n, and for we are computing Cij. How we are going to compute this Cij? Cij plus ai q plus bqj. I mean, we know already this formula. We have seen in the matrices. Just go revise the matrices from the previous lecture, how we are going to multiply the matrices, and then evaluate this procedure whether it is correct or not, right? So then it turns out that this is the correct procedure. But I am interested to find out the time complexity of the matrices here. So what is the time complexity to find out the matrix? Here you can see I is going to run from 1 to m, j is going to run from 1 to n, and then q is going to run from 1 to k, right? And in that algorithm we are going to compute this ci of j, right, for every location. So you can see if this algorithm, this is executing from 1 to n, and in for every I value it is going to run again 1 into n, and for every j value it is going again from 1 to k. So you can simply say that, how many I mean, how many additions of the integers and multiplication of integer are used, I mean, for this value. So there are n square entries in the product. Finding each entry requires n multiplications and n minus 1 additions. So n cube would be the total number of multiplications based on this formula. For n square, n minus 1 is done. For n square, n minus 1 operations are performed. So if you simplify this would be the n cube. So it turns out that a metric is multiplied, two matrices are multiplied in n cube times, right? So let me just give you the one nutshell, one shortcut formula for that, for starting here. From here, yes, this is the first algorithm. So if you have only one loop, so usually it is order of n, right? Order of n. If you have only one loop, if you have an I mean, this is one loop while, right? This is the one loop, so this is order of n, right? Or theta of n, whatever. So so for example here, you have this is a different problem. This is a division problem. This is one loop, but this loop, in this loop, the okay, the difference in this loop is the value is divided by 2. In such cases, the complexity is always order of log n, and base is whatever is the division parameter. If it is divided by 2, this is log base 2. If it is divided by 3, this is log base 3. I mean, you can evaluate this, right? But if the loops are two loops, if you are having two loops, for example, for I is equal to 1 to n, and then inside this loop you are having one more loop for j is equal to 1 to n. So in such cases, the complexity is order of n square. But if you have three loops, right, so you can see the two loops, one loop 2 in the bubble sort. So the time complexity is order of n square, big O of n square, theta of n square. If you have um, two loops, right, for an inside nested loop inside the loop, two loop means the nested loop, one nested loop. So the time complexity is order of big O of n square, or theta of n square, order of n square, right? So if you have one loop, you have big O of n or theta of n. If you have two loop, you have big O of n square or theta of n square. If you have three loops, 1, 2, and 3 loops, so it is order of n cube, right? Or theta of n cube, right? So it depends on, not the number of loops but the nested loops, right? So if there are 4 nested loops, it goes to the big O of n power 4. There are 5 nested loops, this goes to the big O of n power 5. So it means the number of nested loops are basically playing a vital role in the order of growth of your algorithm. So if you want to your algorithm to be less complex, take less time, you need to try to make the less number of the nested loops, right? Okay. So Boolean product algorithm. So this is the same algorithm if you have the 0, 1 matrices and you want to multiply these two matrices. I mean, although there is the number of comparison, since these are the straightforwardly, these are the three nested loops, this would turn out to the order of n cube. But then you can always try, I mean, this is given here that how it is computed at order of n cube. I mean, there are number n square operations, and for every n square operation, you are going to perform the bit operation. I mean, or operation or the and operation, right? So total n cube operations are performed. So how n cubes? I mean, the straightforward method is see the nested number of rules, and you will find out how many number of operations are performed, right? Then the complexity classes, this is I already mentioned in the previous lecture. So this is the constant class that we represent with O of 1. No matter it is the 1000, n is 1000, 10,000, 100,000, whatever, we always represent is theta of 1. That says it's the constant complexity. Then logarithmic complexity, or theta of log n. The linear complexity, theta of n. The linear logarithmic complexity, theta of log n log n. The polynomial, theta of n to the power of some constant. Then the exponential complexity, uh, constant to the power of some variable, right? That is the exponential complexity. And then the factorial complexity, that is exponential to the power of exponential. This is also equal to n to the power of n. And this is the worst ever complexity of an algorithm, right? So this is how actually how much time an algorithm require as the number of input increases in all these complexity classes. So if, for example, this is a linear class, logarithmic class, linear logarithmic, n square. I mean, the square, the this is the polynomial class, this is the exponential class, and the factorial class. If the size of the input is 10 only, right? 10 means the number of input is the size. For example, in order to sort for the bubble sort, for example, so there are 10 numbers in the list that you want to sort. So if the algorithm is log n behaves in the log n time, or the order of the growth of the algorithm is log n, then 3 into 10 to the power of negative 11 is the seconds will be required, right? For the linear 10 to the power of minus 10, for the linear log. I mean, you can see the how many number of seconds are required for the 10 numbers only. So for example, if you have 10 to the power of 5, for 10 to the power of 5, if it is log n behavior, this is 1.7 to into 10 raised to the power of negative 10 number of seconds are required, still into the power of negative n. I mean, very less number of very less amount of seconds, very less amount of time is required, right? And then if it is linear, then still it is 10 to the power of negative 6 seconds, right? And if you see, if it is the square, this requires 0.1 second. And if it is the exponential, you cannot compute even the time of the, I mean, this requires time beyond the computations. So this is I mean, for example, if 10 to the power of 100, right? And I mean 10 to the power of 100, it says static means time 10 required 10 to the power of 100 years, more than 10 to the power of 100 years. So if the input is 10 to the power of 5, and if the algorithm behaves exponentially, right, uh, then it require more than 100 years, 10 to the power of 100 years, in order to compute this algorithm. So that's why we accept the algorithm maximum by the polynomial class. And beyond the polynomial class, we say that these algorithms, for that we may not have the powerful computers in order to compute such algorithms, right? So for the complexity of the problems, we divide the problems in the tractable problems. Tractable problems are, there exists a polynomial times algorithm to solve this problem. Such problems are called tractable problems, right? So for that, if we can find a polynomial time algorithm, remember polynomial time means maximum to the power n to the power of some constant, right? So these problems are said to belong to the class P, polynomial class, right? For that, we can have the polynomial time algorithm. Intractable problems. There does not exist a polynomial time algorithm to solve this problem. So for maybe factorial class problem, maybe the exponential class problem, but such problems are called intractable problem. For that, no polynomial time algorithm is available. Unsolved problems. So no algorithm at all. So no algorithm exists to solve this type of the problem. For example, the halting problem, and we call such problems the unsolvable problems, right? NP class problems. NP problems are the non-polynomial problems, means solutions can be checked in polynomial time. Their solutions can be checked in polynomial times, but no polynomial time algorithm has been found for finding a solution to problems in this class. We can test the problem solution in the polynomial time, but the actual algorithm is non-polynomial, right? That such class is called NP class algorithms, non-polynomial class algorithm. Then there is another class that is called NP complete class, right? NP complete problems are the problems if you find a polynomial time algorithm for one member of the class, it can be used to solve all the problems in that category, in that class. That's called the NP class, NP complete class, right? So these are the types of the problem based on the complexity of the algorithms. Tractable, we have the polynomial algorithm. Intractable, we do not have the polynomial class algorithm, maybe some other exponential or factorial class. Unsolvable, we do not have an algorithm at all. NP class, we can test the solution in polynomial time, but the algorithm is not polynomial. NP complete class, we can if we can find uh, an algorithm for the n for any of the problem in the NP complete category, then that we can find the algorithm for rest of the problems as well. All right. So these are interesting problems, P and NP problems in computer science. So P versus NP problems ask whether the class P is equal to NP. I mean, polynomial is equal to non-polynomial. NP. Remember, in NP class, we can test the solution in polynomial time, but the algorithm is non-polynomial, right? So are these problems whose solutions can be checked in polynomial time but cannot be solved in the polynomial time. So note that just because no one has found a polynomial time algorithm in different form, showing that problem cannot be solved by a polynomial time algorithm, right? If a polynomial time algorithm for any of the problem in the NP complete class were found, then that algorithm could be used to obtain polynomial time algorithm for every problem in the NP complete class, right? So one of the classical example is the satisfiability problem that we saw in the first chapter. So it is generally believed that P is not equal to NP. That is sure. I mean, it is believed, since no one has been able to find a polynomial time algorithm for any of the problems in the NP complete class. So far, no algorithm. So this is really interesting. So the problem of P versus NP remains one of the most famous unsolved problems so far in the mathematics, even in the computer science. So the Clay Mathematics Institute has offered a prize of 1 million for a solution, right? For 1 million US dollars, if someone can find the problem for NP complete class, they they say we will give the 1 million US dollar as a prize money. But so far there is no solution available for the NP complete problem, right? So that's all about this chapter number 3. In the chapter 3, I divided it into 3 videos. In the first video we saw what is an algorithm, and then we saw some example algorithm of the searching and sorting, and then in the second video we saw that what is the growth of the function and how does it grow, and we saw 3 asymptotic notation in there, big O, big theta, and big omega notations. And in this video, the third video, we saw the complexity of the algorithm. Using those asymptotic notations, we can find the complexity of the algorithms, and we saw some examples in this video lecture. All right, so that's all for this chapter 3. In the next week we will be coming back with the next video lecture. Until then, take care and bye bye.